My email ID, in case any of you want to contact me, it's just my name, Mukesh Chadha, at name of my company, which is Tata Elxsi. Just be sure of Elxsi to be done properly, because a lot of people make mistakes on that. Okay. Otherwise, if you want my personal ID, it's just the name dot and at yahoo.co.in. So you can utilize any of that. That is mukesh.chadda at yahoo.co.in. So you can do that. Now, designing systems with Rtos is a, what should I say, a complex job. Okay, especially when we come to the real-time environment. Now, I cannot do justice to that in this 50 minutes, but what I have tried to do here is take some of the normal mistakes which inexperienced designers do here. Okay, so that we can, if we can avoid those design problems, then our designs will be much better. Now, in this case, what is it we are doing here is, the topics we will cover is task allocation in the multitasking system. How do we allocate the task and what problems we could face there? Subsequent to that, we will take a look at it, our critical regions. Okay, what are the critical regions? How do we take care of those? Then we will talk about is the interrupts. A lot of people are scared of interrupts. We will see how to avoid mistakes in that. And then we will talk about is the watchdog timers, their usage and what precautions we should take. And then last will be system-wide priority allocation. Okay. So these are the topics I will cover. Now, first, of course, I am assuming that all of you have some background on these things, because otherwise it's difficult for me to present. Now, task allocation, if you see, okay, multitasking, as we know, it's a fundamental mechanism for us to make work in the real-time system. So that now only problem is, depending on the number of CPUs, even if you have, let's say, 40 CPUs or 64 CPUs, even then the number of tasks could be greater than that. So it's always, it is a illusion that everything is happening in parallel. If you have only one CPU, you may have 20 different tasks, and it will be one task which will be executing at a given point of time. But if you can do it fast enough, then you will never feel the absence of CPU resources for you. So concurrent execution of tasks, and each task we will like to give it a priority. Now, the task will have the separate context, because when I am moving from one task to the other task, I may have to come back to this task sometime in future, in which case I must restore its context whenever I am going to switch out, so that when I bring it back, the entire context can be saved. Context includes what? All the CPU registers, my program counter, stack pointer, then we will see here the time which we had allocated to it, and so on. Now, all these informations, OS control information, these are saved in what we will call as the task control block. Okay, there are various names given. If you are seeing some of the documents may use as a process control block, task control block, or by some other name, it doesn't make much of a difference for us. Now, whenever you are doing the context switching, okay, what is it we will have to do? The kernel must save the context of the old executing tasks, because we have to come back to this, and then load the context of the new task into the system and start running. Now, where the problem comes, okay, the first thing is how many tasks we should have. Now, depending on the experience of the engineers, if you ask them, okay, if somebody who has come new, he will say that either one end they will say that as many tasks are there. Somebody will say 500 tasks, 600 tasks. And some of them who are inexperienced, who are used to normal C programming, their viewpoint is just one task should do, because I have been writing one program and one should do. Now, both these are limits on the other side. Both of them are not suitable for us. Now, what is the problem? If I have too large number of tasks here, okay, they will result in overheads. In what way? Every task when I am doing the, supposing my code is only 5,000 lines. And if I have got 5,000 codes on an average, every time you execute one line of code, you have to do the context switching. Which means what? and the context switching is a dead time for us. It doesn't help us in any way. So my overheads will be high, my programs will run much slower rather than running faster. On the other hand, there is another problem with that. So if I have task switching and then memory required, because every time I create a task, it's a controller structure has to be done in the TCV, which is all the processor registers, stack we have to allocate, priority we have to allocate, and so on. So if I have 5,000 tasks, 5,000 task control blocks will be existing for me. So initially the engineers who are inexperienced, they will create a lot of many tasks with that, and then you will find either you run out of the memory or context switching is being done so often that the programs are running very, very slow. Now the point is, what should we do about it? Okay, so and if somebody is doing a smaller number of tasks, then what happens is in the middle of the task when we are, that is the time we have to do. If somebody requires, let's say this is the point I have just crossed and there is some request here. I can attend to this request only when I complete my entire task and then come back and look at it. And that is the problem with we will call it as a unitasking problem, or if you have less number of tasks, in which case my response to the real-time events again will come down. So the question is, what should we do? So we have to do obviously a balancing act. We should create number of tasks. Now how do we create the tasks? Tasks are created on the various ways. Okay, so this will be, number of tasks should be small enough to give the desired response. Okay, at the same time they should be large enough to take care of requirements of partitioning between various other things. So it's always, there is no fixed answer. It will depend on your application, and then based on your application you have to decide how many tasks you should have. Typically, even in a complex system, about 25 to 30 tasks are the maximum you should have. Preferably will be somewhere around 10 or 15 of them. We will see later because the task will be, these are pure application tasks, but we will have tasks associated with the interrupts and so on also. Now, next problem where we find problems are the critical regions. Now, critical regions are what? Where there is a data structure, okay, and more than one task are trying to simultaneously read and write onto that. Now, if I don't provide a lock onto that, then what happens is, let's say I want to, a file is there, and the file is being edited by 3 different people. Now, a one word somebody has done halfway, somebody else comes with a higher priority, he is allowed, he edits some other part, then you come back to the first fellow, okay, he might modify what has been edited later. So this is what we will say critical regions, where the data integrity is of importance to us. And let's see how we will maintain that. So in the critical region, there are various ways of managing that. One of them is resource locking with a semaphore. So I'll create a semaphore which is a primary object, and I will make it empty, and then I'll ask for that. Okay, in this case, for when I am handling the critical region, the semaphore will be full, and I will ask for the resource. And once I get the semaphore, then I am allowed to modify that. Once I finish my work, I will release the semaphore. In between, if somebody is asking for this resource, then he will not get it and he gets blocked. So that is how we can prevent utilizing the semaphore. However, this may involve interrupts also, because a lot of times the data which come to us come from the interrupt sources. In which case, when I am working on this critical region, I may have to block my interrupt also. Okay, so that's again another requirement. And then we have a lot of times, now see what happens is, whenever I am doing this, a task is requiring something, he has taken already the semaphore. Next task comes, it tries to take the semaphore. Once the next task is taken, he is not getting it, so what happens is he is swiped back. Now I have done 2 context switching. Now if my work is very small amount and it has to be done very frequently, then what happens is I will spend more time on the context switching rather than onto the actual work. In which case, my third option comes is where I will lock the scheduler itself. I will lock the scheduler, perform my work because work is for a very small duration, and then enable the scheduler once more. So these are 3 methods where we will be having that. Now I will talk about each one there. So mutual exclusion semaphore is created to guard a critical region. They usually offer the deletion safety. That is, if somebody has taken this semaphore, that task will not be deleted. Because if you can delete that, then what happens is this resource is permanently locked, nobody can use it. Okay. Now this deletion safety you have to do. So a lot of times people don't use the deletion safety, and in their programs, you delete, somebody gets deleted, deletes the task, and then nobody can handle this. Okay, that region is logged out for us. Then we have priority inversion problems. So normally these mutual exclusion semaphores will use what is called a priority inheritance algorithm, which is very simple. I am here now. Let's say my CO comes, he wants the same resource. Let's say he also wants to present this, but I have already taken the semaphore. He cannot do that. Now, in between, so he is waiting, somebody else who has got a higher priority than me, he doesn't want to do on that, but he wants this laptop. He can take off the laptop. Then what happens? Neither I can work nor my CO can work. Okay, so to prevent these kind of conditions, what we will do is, we will inherit the priorities. So the moment he wants the resource and I am holding it, then my priority becomes his priority. Okay, I inherit his priority, and then the mid priority task or whatever is the lower than his priority, it cannot interrupt me, and I will complete my work and get out of that. So a lot of times people fail to use the inheritance algorithm, which is an option, and then you will have problems where you will be seeing that your system is not working appropriately. Semaphore is initially available, so sequence will be semtake, operate on the critical region and give the semaphore back so that somebody else can use it. Now, a lot of times people put critical regions as a huge mass of data. Never do that mistake. Why you want the critical region to be short? Why? Because till I get out of the critical region, nobody else can operate on that. So let's say, for example, an employee database, and all the data are critical. But I will not make my entire database critical. When I am updating one record, only that record I will make it critical, operate on that, release it. So that if some other higher priority task wants to operate on that data, he can do that. Okay. So we should always keep the critical regions as short as possible. Now, locking out preemption. Okay, we use the commands or similar things all the operating system have got, task lock, task unlock, and in between the critical region. Now, here also the critical region should be very short for you, because what you are trying to do is you are preempting the scheduler, which means what? Scheduler will not allocate any other task. Now, a very high priority task also may come up. You will not honor it because scheduler is locked. So the idea here again is my critical region should be as short as possible. Now, if it is large, what will the one thing we will get here is the poor real-time response. Okay, why? Because some higher priority task has come. It has nothing to do with this critical region, but he will not be allowed to run on to that. And second thing we have already said, higher priority task cannot execute even though it's not involved with the critical region. Now, next thing is of course with the interrupts. Okay, so we must disable the interrupts. We will say interrupt lock, and then you finish your work in the critical region, and then disable the you release the interrupts. Now, only problem is if critical region is large during that period, no interrupts will be honored for you. Okay, so again, my critical region should be as short as possible. So this is again another problem we face. Okay, so in this case, what care we should take? Must identify all critical regions. A lot of times when you are examining a system, it may be difficult for you to identify the critical region, and if you have missed out something, overall you will find a data corruption will take place for you. Okay, so you have to be careful of, in your analysis phase, you must deliberate and find out all critical regions for you. Then, use appropriate methods depending on requirements. If there is no need for you to lock the interrupt, don't lock it. Okay, if scheduler, if the work is of a larger duration rather than a short duration and to be done infrequently, never attempt the locking of the scheduler. So if you do that, you won't have any problem on this. And then of course we have said everywhere, keep critical regions as short as possible. Now interrupt handling. Okay. Now interrupts we know that is the CPU's way of recognizing some response which has to be given. Somebody has made a request, so that request travels to us through the interrupts. So usually what will happen is a user defined routine is installed to execute when an interrupt arrives. This routine will run at the interrupt level of that. It's not a task, please remember. Almost all operating systems, real-time operating systems you will have. Idea is what? When an interrupt task is running, no application task will run. Okay. Now, what is the point here? Interrupts, whatever work you are doing, it should be very short. Right? Because application is not running within that time. And if you are going to have a large interrupt program, then during that, no lower priority or equal priority interrupt can interrupt you. So your idea should be what? To get out of the interrupts as fast as possible. Interrupt service routine. Now, my thumb rule is if you're writing more than 2 instructions in the interrupt service routine, there is something wrong. What you have to do is save whatever data has come to you and get out of the interrupt. Do the processing somewhere else. Okay? We'll see how we will do. Interrupt handling does not involve task switching because it's done totally in a different context itself. So what we do, typically we will create a binary semaphore. Every interrupt will have one semaphore value is empty. Then we'll attach an interrupt service routine to interrupt handler, create a task to process the event. So there is another task which will do all the data handling part of me. In the interrupt service routine, I will just take the data, store it, and give a semaphore to this task. That's my end of the interrupt handling. Now, when I come to the interrupts, this task which is responsible for me to execute this work, whatever priorities are there for him, he will come with those priorities. Now the advantage of this is because you are getting out of the interrupt service routines fast, even the lower priority interrupts will be able to interrupt you. However, those programs may not run immediately because it will depend on the priorities. So the tasks, whatever we have created, it will block on the binary semaphore and will execute when interrupt service routine is given for me. It gives the semaphore. Now restrictions, a lot of times people forget that. In an interrupt service routine, you see, while interrupt service routine is being run, tasks are not running. You must never do anything which will block you. At the same time, you should not use creation and deletion routines also. The reasons are very simple. If you block yourself during the interrupt service routine, there is no way for you to get out of that. System will just hang for you. And this is one of the very frequent problems we get. Somebody asks, malloc, memory is not available. Just blocked. Interrupt service routine is blocked, task is not running, system is dead. As simple as that. So, never do anything which will block you. You should not take a semaphore, okay, because semaphore may not be available and hence you will get blocked again. ISAs cannot call any creation or deletion routines. Deletion routines, most of the time you might be able to get away with that, but sometimes a task might have made itself safe from deletion. You try to delete it, you will get blocked. You are blocked, whole thing hangs. Okay, creation is usually a time consuming job. Okay, because you have to get and you may not be successful also. That's again another problem. You say create task. For that he has to allocate memory for the stack, he has to allocate memory for the TCB, create those structures, fill them up, and then start your task. Okay, which is time consuming. Now you can imagine you are going in an automobile, you are pressing the brake, and if you have not executed your task, and that is the time you say start brake task, by the time he finishes, creates the task, there may not be any need for that task, right? Because hardware itself would have gone along with the person who was driving it. Okay, so that's why we never do this creation or deletion of the routines with that. Now guidelines, keep them short, okay, because if you don't, then it will delay lower and equal priority interrupts, it will delay all tasks because tasks will not be running. It can be hard to debug. Interrupt problems are always hard to debug for us. Then avoid floating point operations in the interrupt service routines. Usually never perform them in the interrupt service routine. More than 2-3 instructions, there are exceptions, but if you are going to do that, you must know why you are doing them. Okay, floating point because these instructions take a very long time, so we will never execute them in the interrupt service routines. Try to offload as much work as possible to some other task which is of longer in duration and less critical for us. Now, watchdog timers. Watchdog timers normally will have two types, hardware watchdog timers, software. Of course, what we are talking about is here is the software watchdog timers. And these watchdog timers are created to watch over your system, basically the execution. If some task goes into an endless loop or something and you want to recover from that, this is the only way you can get out of that. So we will use the watchdog timers in that. What they will do is it allows me a C routine to be executed after a specified time delay. Upon expiration of the delay, connected routine will run, okay, which is run in the OS context. Please remember that. Okay, and hence we will see what are the precautions we will. So watchdog timer, what you can do, you can create them, you can start them, you can restart them, you can delete them. Okay, so let's say one of my tasks is taking normally 5 milliseconds to execute. Now what I will do is I want to make sure that it finishes at least in, let's say, 7 milliseconds. Okay, so what I will do, I will attach a watchdog timer. I will start a watchdog timer, and before the 7 milliseconds, the task should have completed its work and reset the timer. If it doesn't reset, then watchdog timer will elapse and it will trigger the C routine which is attached, and this C routine will be your error recovery routine. And that routine will run and then bring your system back to whatever you want to do in your error recovery, you will do there. Now, what are the precautions? The implementation is similar to interrupt service routines because they run in the OS context. So first thing is again the same, you should do less work there, and also you must never do anything which will block you. Because just like interrupts, if you get blocked here, again your system will hang. Usually we'll give a binary semaphore as a response to this interrupt service routine, and just like for interrupt, we had created an interrupt handler for each of the interrupts. For each of the watchdog timer, we will have a error recovery routines. So typically in watchdog timer routine, I will just release a semaphore, and my other routine was all the time waiting for the semaphore. It will get the semaphore once I come out of the watchdog timer, and then he will run. The problems here are what? People will start that, but a lot of times they forget to cancel the watchdog timer. Now what happens is, timer doesn't know. Okay, so you don't cancel it, then after it's a predefined time, it will run, and it's as though error has happened in the system, and it will start error recovery routine. So that's again another problem. Some people also try to use these watchdog timers as a normal timer. Never do that. Okay, because the purpose of these are totally different. Okay, so if you want a timer, you must use your hardware timer or some other timing mechanism rather than these. The last part in this is the priority allocation. Now the problem is what? We have got a system now. In the system, I have to do all my, so many things are there. I have to take care of my interrupts, I have to take care of my OS, I have to take care of my application, I have to take care of my watchdog timer. How will I go about allocating the priority? Because if you miss on your priorities somewhere, then your system will not work in a proper way. So let's see how we can do that. Now, major areas, if you see, are what? User task, which is basically your application which is running. Then there will be some interrupts. Okay, if my system has got, let's say, 8 interrupts, for each of them, I will have task with some activity has to be done. So that is again another thing. Then watchdog timers. How many watchdog timers I can have? It depends on my system. Some system, one may be sufficient. In some system, I may have 50 of them. I may not use all of them at the same time. Okay, but availability might be there. So then there will be certain OS tasks which will be created, because all these, your application will run under the control of the OS. So OS will create some task for you which will help you in your execution. Say for example, error recovery task or a log task, which are the system tasks that. So these are the normal work which we'll do in the real-time environment also. So how do we get that? So first thing is OS tasks required for application is specific. OS will allocate these priorities. You must go through the documentation and find out, never meddle with those. Return them as it is. In the sense that don't change their priority. Okay. In some cases you might be allowed to do that. Other than that also, don't use those priority for any of your tasks, because if there is a conflict, okay, you don't know which is causing problem for us. So we will never do that. We'll leave it as it is. Then next will be Watchdog Timer related task. Why? Because this is an error recovery for me. This is the next important aspect for me. So I will allocate a band of priorities for it. Okay, depending on how many Watchdog Timers I am going to use, I will allocate so many priorities at the next lower level of priorities. Then next level will be, okay, so the task related to Watchdog Timers will have next set of priorities, distinct priority for each Watchdog task, and then we will have an interrupt related task with that. Okay, so depending on the number of interrupts I have, for each interrupt I will have one task for me. Then having done that, then I will come to the user task. The application task can be given the remaining priorities for us. Okay, and then the application task will have the priorities can be distinct, okay, depending on the priority levels, or it could also be shared priorities, because a lot of times we don't want the two tasks to interrupt each other, in which case we will give them the same priority. Okay, so, and that will of course depend on the project requirement. So allocation of the system-wide priorities, we will go in this order. How many priorities you require? Normally the systems we have been using, there is a byte which is allocated, 256 levels of priorities are there, which are much more than enough for you to handle all these activities for you. Alright? So okay, so that's my end of my presentation.